Hello everyone. I'm Dr. Michael, and we're starting a new series called Celestial Chronicles. In this series, we'll talk about amazing discoveries and research that you can only learn about by reading thick and boring scientific journals like Astronomy and Astrophysics and others. But behind the maze of numbers, graphs, and formulas, there are real treasures of our universe hidden. As it turns out, the life of our universe is filled with incredible stories and dramatic events, where there's life, tears, love, and death.
Let's dive into the fascinating world of the Gaia mission, an ambitious astronomical endeavor that has gathered astrometric data on over 1.5 billion celestial sources. But here's the catch: only the brightest 34 million of these stars had their radial velocities measured. That is, until now. A groundbreaking study aims to push these boundaries further, extending these measurements to an impressive 220 million sources. Using Gaia's low-resolution spectra, researchers have developed a novel methodology that fits these spectra with synthetic models to estimate radial velocities. This approach not only increases the volume of data but also tackles the challenge of systematic biases by correcting them with external radial velocity catalogs. The payoff? The introduction of a new catalog featuring radial velocity data for around 6.4 million sources. This is just a teaser of what's expected in Gaia's future data releases, which could revolutionize our understanding of the galaxy by potentially expanding radial velocity measurements to nearly 2 billion sources. However, as with all scientific endeavors, there are limitations. The radial velocities derived from this method have higher uncertainties compared to those obtained through high-precision instruments. But the value of increasing the number of measurable stars far outweighs these drawbacks, providing a richer, more detailed map of galactic dynamics. As we look to the future, the continuous refinement of these techniques promises to sharpen our view of the cosmos, offering deeper insights into the complex structures and dynamics of our galaxy. This advancement in galactic studies is not just a step, but a giant leap in understanding the vast universe we are part of. Stay tuned as we unravel more mysteries of the cosmos with the power of Gaia's extended data.
Who among astronomers, or even just well-informed people, hasn't heard of Delta Cephei? It's a true celebrity in the world of stars, giving its name to an entire class of stars, Cepheids, pulsating variable stars with a stable period and known luminosity, which makes them incredibly useful for measuring distances. And now, it turns out that Delta Cephei is a binary star system.
We have an exciting update on the Delta Cephei binary system, brought to you by a recent study published in Astronomy and Astrophysics. Delta Cephei is a classical Cepheid variable star, known for its importance in measuring cosmic distances. Recently, an inner companion to Delta Cephei was discovered, sparking interest in understanding its orbital parameters. To get precise measurements, scientists utilized the HARPS-N spectrograph in 2019, gathering new radial velocity data. So, what did they find? Using a reference template from previous studies, the team calculated the residuals between the new data and this template. This allowed them to determine the orbital velocity of Delta Cephei. They then employed a Bayesian tool to refine the orbital parameters, incorporating constraints from the Gaia mission. The results are fascinating. The orbital period of the Delta Cephei binary system is approximately 9.32 years, with an eccentricity of about 0.71. The semi-major axis measures around 0.029 arcseconds, and the center of mass velocity is approximately -17.28 kilometers per second. These refined parameters enable scientists to create a cleaner radial velocity curve for the pulsation of Delta Cephei, which is crucial for future research. Let's delve into the data. Between June and September 2019, 24 HARPS-N spectroscopic measurements were taken, spanning 13 pulsation cycles. This extensive data collection has been pivotal in achieving these precise results. The study's success in refining these orbital parameters opens new doors for understanding the dynamical structure of Delta Cephei and its role in astronomical distance calibration. Looking ahead, future observations, particularly from Gaia's upcoming data release, are expected to provide even more constraints and insights. Stay tuned as we continue to explore the cosmos and unravel the mysteries of the universe.
Cosmologists are scientists who are interested in what the future holds for our universe. Right now, they are grappling with the problem of missing mass in galaxies. And this isn't about dark matter. Even the visible mass of ordinary matter doesn't add up to explain why galaxies and clusters behave the way they do. We present to you the latest research in the quest to find this missing mass in the spiral galaxy Messier 83.
Scientists have recently turned their telescopes towards the Messier 83 galaxy group, a neighbor of our Milky Way, to explore the abundance of dwarf galaxies surrounding it. This research aims to test the widely accepted lambda-cold dark matter model, or lambda CDM, which predicts how structures form and evolve in our universe. Previous studies have highlighted issues like the missing satellites problem, where fewer dwarf galaxies are observed than predicted, and the too big to fail problem, where simulations suggest certain large galaxies shouldn't exist. This new research employs two cutting-edge methods, cosmological simulations that include baryonic physics and theoretical predictions from the subhalo mass function. The team identified 13 confirmed dwarf galaxies and 8 potential candidates within 330,000 light-years of the Messier 83 galaxy using advanced distance measurement techniques. Their goal? To compare the observed data with predictions from the lambda CDM model. Using the state-of-the-art Illustris TNG50 simulation, researchers found that while the number of bright satellites matched predictions, the number of faint satellites was significantly underestimated. This discrepancy highlights a too many satellites problem for the Messier 83 group, suggesting that our models may not be as accurate as we thought. The second method, applying the subhalo mass function, painted a similar picture. It predicted the number of dwarf galaxies by assigning stellar masses to dark matter halos. The result? A significant gap between observed and predicted numbers, especially at lower luminosities. These findings reveal that the lambda CDM models underestimate the number of faint dwarf galaxies by a significant margin, challenging our current understanding of galaxy formation. The study emphasizes the need for continuous testing and refinement of our cosmological models. It's a fascinating time in astronomy as we push the boundaries of our knowledge and uncover the mysteries of the cosmos. Stay tuned for more exciting updates from the world of science.
From distant stars, we return closer to home. There's plenty to talk about here as well. We've all heard about the asteroid Ryugu, visited by the Japanese Hayabusa 2 mission. And here's what they found there.
Recent studies, including the latest research by a team of international scientists, have shed light on the intricate processes shaping the surface of Ryugu. This near-Earth asteroid, which was extensively studied by the Japanese Hayabusa 2 mission, reveals significant evidence of thermal fracturing. This process, caused by the extreme temperature changes as the asteroid rotates and its surface alternates between sunlight and shadow, leads to the formation of fractures in the boulders on its surface. The research involved analyzing high-resolution images taken by the Hayabusa 2 spacecraft. These images were used to map and measure the orientation and length of fractures on Ryugu's boulders. The findings show a predominant north-south alignment of these fractures, suggesting that thermal stress is the primary cause of their formation. What's particularly interesting is the estimated timescale for these fractures to develop. The study indicates that it takes about 30,000 to 40,000 years for these fractures to reach their observed lengths. This rapid geological process highlights the dynamic nature of asteroid surfaces and provides valuable insights into the evolution of these small bodies in our solar system. Comparisons with another well-studied asteroid, Bennu, reveal similar patterns, reinforcing the idea that thermal fracturing is a common process on airless bodies. This research not only enhances our understanding of asteroids, but also aids in our broader comprehension of the physical processes that govern their evolution.
Hypervelocity or high-speed stars are a truly unique phenomenon in nature. Imagine a Formula One car speeding through a regular traffic jam. That's what hypervelocity stars look like on the galactic highways. But their astonishing speeds, reaching hundreds or even thousands of kilometers per second, are almost always the result of a dramatic event in their lives, like a nearby supernova explosion. Our next story is about such a hypervelocity star.
Tonight, we bring you an extraordinary discovery in the realm of astronomy, the remarkable story of the high-speed star, GHS 143. A team of international astronomers has delved deep into the mysteries of this extreme speed star, uncovering fascinating details about its chemical composition and binary nature. Using the powerful UVES spectrograph at the Very Large Telescope, they have revealed insights that could change our understanding of stellar dynamics. GHS 143 is no ordinary star. Identified as a single-spectrum spectroscopic binary, this star's radial velocity variations indicate it is part of a binary system. This discovery challenges previous assumptions made by the Gaia Data Release 3, which treated it as a single star. The star's parameters are equally intriguing. With a low metallicity and an ion abundance of FeH equals -1.74 dex, GHS 143 presents a unique chemical fingerprint. Its surface gravity is determined to be around 2.1 dex, suggesting the star is closer and less luminous than previously thought. But what truly sets GHS 143 apart is its chemical composition. The star is poor in carbon but rich in nitrogen and oxygen, with a strikingly high C+N+O Fe ratio of +0.65. Enhanced in alpha elements like magnesium, silicon, and calcium, GHS 143's elemental abundance patterns offer clues to its origin and history. These patterns suggest that GHS 143 may have formed in a dwarf galaxy later to be captured by the Milky Way. Its young apparent age and high mass reinforce this theory, indicating a star that has traveled across the cosmos. Kinematic studies reveal that depending on its parallax, GHS 143 could be unbound from the Milky Way, making it a stellar wanderer in our galaxy. This groundbreaking research not only sheds light on the nature of high-speed stars but also enhances our understanding of galactic dynamics and the complex.
The Delta Cephei binary system, the dwarf satellites of the Messier 83 spiral, the hypervelocity star GHS 143, these are just a tiny fraction of the immense, universe-sized collection of objects that teams of scientists study. These scientists are armed with fundamental knowledge, have access to the most advanced scientific instruments humanity has ever created, and are filled with boundless imagination and, I'd even say, the boldness to hypothesize, to invent, and to ask the right questions. We're living in the most exciting time in the science of the universe, as humanity rapidly expands the boundaries of its knowledge and unveils the once hidden mysteries of space. Stay with us to learn more about the incredible news from the world of science. Thank you for your attention. Good night. The sky is big enough for us all.